Okay, so in this video, I just want to talk about voltage division or voltage divider circuits, and that is basically when we have a bunch of resistors in series. So a bunch of resistors connected from head to tail in line coming back to the source. So let's start off by just drawing a voltage source here with some wires. And let's say that this is a 6-volt voltage source, and this is our positive and negative terminal. So we have a wire connected from the positive terminal coming over here, and then there's a gap. And then this other wire comes back and connects to the negative terminal. So in this case, where these wires don't form an actual connection, we call this an open circuit. And according to Ohm's law, which is V equals IR, well, we can rearrange for I to have that as voltage over resistance. Then in the case of an open circuit, we treat this break as if we have an infinite resistance. And when you have a fraction where the denominator is tending to infinity, then that's going to make this number very, very small. And basically that's going to, as this tends to infinity, then the current is going to tend to 0. So for an open circuit, we have no flow of electricity. Now, if we have the opposite, where we just connect the terminal with a wire, like this, then this is what we call a short circuit. And because we model our wires as having 0 resistance, that means that basically our resistance here is going to tend to 0. And when you have a 0, basically, or something approaching 0 in the denominator of a fraction, it's going to make the number very big. So as we approach 0, then our current approaches infinity. So we treat closed circuits as if they have infinite current, which is a dangerous situation and something that we definitely don't want to have. So what we normally do is we add in resistors to the circuit, which limit the amount of current flowing out of the voltage source. So when we look at this, the voltage drop across the resistor is 6 volts, and that's because this whole top wire is connected to the positive terminal of the voltage source, and the positive terminal of the voltage source is 6 volts higher than the negative terminal, and this wire, the blue one, is all connected to the negative terminal. So everything on the red node is 6 volts higher than everything that's on the blue node, and that includes this point being 6 volts higher than this point. So that's the voltage drop in Ohm's law, and then the resistance is just what we have, is 2 ohms. And then in this case, we would find that the current is just equal to 3 amps. But what happens when we have multiple resistors in the circuit is we have to find an equivalent resistance. Now, if we just think for a second here, let's get rid of this to free up some space. Then let's imagine we have this point here. Let's call it point A, and another point down here. Let's call it point B. Then let's just remove the whole right-hand part of the circuit and bring it over to the right just for a minute. Okay. So all of the current that was going to flow through this section has to be the same amount of current that's flowing out of here and the same amount of current that's flowing back in. Now, there's more than one thing that could cause the exact amount of resistance that's over here. So really, we could just replace this with a single resistor that has the same equivalent resistance as all 3 of these together. So if we just drew on one here, and we can call it R equivalent, as long as when we connect it to point A and B here, that it gives us that same amount of current flowing that it would have if it was flowing through all 3 of these, then the voltage source honestly doesn't care what's actually going on over here, whether it's one equivalent resistor or 3 individual ones. And it turns out for simple series resistors like this, where all the resistors are just in series with each other, connected head to tail, that it's just the sum. So we have this. So the equivalent resistance is just the sum of all of the individual resistances. So in this case, that is just equal to R1 plus R2 plus R3. And we have these numbers, so let's just fill them in. So we have 0.5 plus 2 ohms plus 1.5 ohms. So that means our equivalent resistance is just 4 ohms. So we can solve for the total current in the circuit that's basically coming past the voltage source. It is I, and this is equal to V over R. And if our voltage drop is 6 volts and our equivalent resistance is 4 ohms, that means that we just have 6 volts over 4 ohms for a total of 1.5 amps. So again, if we have a 6-volt voltage source, whether we have this situation where there's a single resistor of 4 ohms, or we set it back to how we were before with the 3 series resistors, then we're going to have, in this system as well, 1.5 amps flowing through. But let's actually draw a ground on this circuit right here. And so the ground is going to serve as our reference for what we're considering to be 0 voltage. And then if we go and label on or shade in basically some nodes here, so we have 1, 2, 3, and a 4th node like this, then we can label on the voltages with respect to ground. So the blue node here is 0 volts. The red node is 6 volts because it crosses the voltage source. It jumps 6 volts from the blue side to the red side. When we come from this point to this point across this first resistor, we can find the individual voltage drop here, also using Ohm's law. So that's just going to be equal to V1 is equal to I R1. So we have 1.5 amps times 0.5 ohms. So that gives us the voltage drop across resistor 1 to be 0.75 volts. So it's a drop of 0.75 volts. That means we have 6 volts here. It's going to drop by 0.75 for 5.25 volts, which is the voltage of this whole green node with respect to ground. And then we can check the voltage drop across resistor 2 as well. So we just do Ohm's law again, and we have V2 is equal to I R2, and the current is going to be 1.5 amps as well because it's all flowing through the same line. Basically all 1.5 amps goes around the circle. So we multiply that by the resistance, we have 2 ohms, and we get a voltage drop for V2 of 3 volts. So that means that this pink node here is 3 volts less than this green node, and 5.25 minus 3 is 2.25, so we can label that on. It's 2.25 volts. That's the voltage, total voltage basically with respect to ground, or basically it's saying it's 2.25 volts higher than ground. And if we were to check the voltage drop across resistor 3, we would have V3 is just equal to I R3, which is 1.5 amps times 1.5 ohms, and that gives us the voltage drop of 2.25 volts, which is good because it's saying that it drops from this side to this side, value of 2.25, and 2.25 minus 2.25 is 0, so we actually end back up with 0 volts, which is what we're expecting. So anyways, as you go around the circle like that, that's actually referred to as Kirchhoffs voltage law, that you should return back to the same voltage that you started with in a single loop. And that's exactly what's happening here. So the total voltage of this voltage source is 6 volts, and the voltage drops get split up among each of the resistors. So we had 0.75, 3, and then 2.25, and when you add all of those together, that's a total of 6 volts, and it's basically being divided across the circuits, and that's why we call it a voltage divider circuit. So each resistor has the same current flowing through it, but a different voltage drop, and they all add up to the total voltage of the voltage source. Okay, cool. That's enough for this intro, and I will see you in the next video, and we'll go over another example of a voltage division circuit.